Next area we're going to get into is forces and how forces affect motion. We're going to get into this more with Newton's laws next unit. But a force is a push or pull that one object exerts on another. All right, so that is a definition that we need to know. A force is a push or pull that exerts from one object on another. It is a vector. All right, remember, a vector requires a direction. All right, and the way we measure force is measured in newtons. All right, so it would be, anytime I ask you about a force and I say how much force is acting on an object, your answer needs to be in newtons. All right, so force is measured in newtons. All right, so what forces are acting on an object? I mean, really, once again, I'm going to ask questions like, hey, what force is acting on this piece of paper here? Well, forces are always acting on objects. All right, so if you say no forces are acting on objects, it's just wrong. Okay, so never, that'll be one of the options when I ask you. It's never no forces acting on it. Because there's always gravity, there's always a downward force of gravity, and then there's going to be an upward force exerting on an object as well. So there's forces always acting on an object in here. So a force, when a force and a net force is applied, and we're going to talk about this a ton, a force, that's not what I wanted to do. A force causes an object's motion to change. A force, in other words, what that's saying is that a force causes acceleration. All right, so when an unbalanced force acts on an object, it's going to cause its motion to change. It's going to cause it to either speed up, slow down, or turn. And that should make sense. If I walk up to something and I push it, and I supply an unbalanced force, I push it harder than what? I push it hard enough to get it moving, then it's obviously going to accelerate. All right, so an unbalanced force is going to cause the motion of an object to change. It's going to cause acceleration, and we're going to spend a lot of time talking about that in the next unit. But we'll talk about it some here as well. All right, and there's different terms in forces. So a net force, when I use the word net force, this is going to be a term we have to know as well. A net force is a combination of all the forces. All right, so a net force is a combination of all the forces. A balanced force is when the combination of all those forces are balanced, they're even. You think of it as a scale or something where you have both sides are completely balanced out. All right, one side's not more than the other. So here's an example of a balanced force. All right, I have good old Jane and Mehmet pulling on a rope, both pulling with 100 newtons of force. Mehmet's pulling with 100 newtons back at him. Jane's pulling 100 newtons back at her. So then our net force, since force is a vector, our net force then is going to be 0 newtons. Okay, because it's 100 one way, and since there's 100 going in the opposite direction, it's a vector. Direction matters. So since it's going in the opposite direction, all right, we're going to subtract those two. So we're going to combine the forces. So we have 100 going one way, positive, 100 going the opposite way, which is negative, and so they would cancel each other out to be 0. So since there is no unbalanced force acting on it, they are not going to be accelerating. All right, they're going to be staying right where they're at. All right, since they have the same force acting on it. All right, and then let's say if I make this instead of 100, let's make it simple. Let's say good old Jane, she's been working out. She's 400 newtons of force. All right, so I can't erase that for whatever reason. Jane has 400 newtons of force to Mehmet's 100 newtons of force. All right, so now there is a net force, F net, acting on the object. It is 300 newtons back toward Jane. And so as you can imagine, once again, we said a force causes acceleration. So what's going to happen if Jane pulls with 400 newtons of force compared to Mehmet's 100? Mehmet's going to go for a ride. He's going to get pulled. They're going to be accelerating. They will be accelerating in that direction. And this is going to be important to know too, because we're going to talk about this with Newton's laws. An object's going to always accelerate in the direction of the net force. And that should, once again, that should make sense. I walk up and kick a ball. If I kick a ball north, it's not going to go south. It's not going to accelerate it the opposite way I apply the force. So that should make sense. That objects accelerate in the direction of the net force. All right, and so a balanced force would have been the previous example where they're equal. An unbalanced force occurs when there's a combination of forces that are not equal, when the net force is not equal to 0. All right, so it's not equal. A balanced force is when they are equal. All right, and so these are so balanced force, net force is 0. Unbalanced force, once again, is not 0. All right, they're not balanced. They're not the same. Other things that can factor in is friction. Friction is anything that can oppose the sliding motion between when two surfaces are in contact. All right, so friction is a force that's oftentimes when you push something, it's a force that sometimes it's hard to quantify. But we'll talk about that quite a bit as well, where friction is a force that opposes that sliding motion. Here it just talks about what causes friction. I'm actually not going to get into it too much. But basically, the frictional force, these microwells form between the two surfaces. They stick together, causes friction. Because no surfaces are completely perfect. They have little grooves and bumps and dips. And so when they come into contact, that makes it difficult. And then it says the friction force between the two surfaces increases when the force is pushing the surface together increases. All right, and that once again, that means heavier objects are going to create more friction. It's going to create more friction between the surfaces. They're going to be harder to move. Different types of friction. There's static friction. That's where the frictional force prevents, so it's so great that it prevents it from sliding past each other. Sliding friction is when it's already sliding. It's already in motion. And then rolling friction, and this is usually the lightest, the least form of friction. And you just think about that. If you ever try to move something, if you ever try to move anything, rolling friction, when you put it on wheels, it's a lot easier. If you ever get like a hand truck or a dolly or whatever you call them, you're trying to move something heavy, you put it on wheels, man, that thing just goes right away. It's super easy because rolling friction is much less than sliding friction because there's less surface contact. If I'm trying to push a big box across the ground, that whole box is in contact with the surface. If I put it on wheels, only the wheels are in contact with the ground. So there's very little surface area that is in contact, causing the friction to be less. So that's why rolling friction is better. And then there's other types of friction as well. There's air resistance. Air resistance occurs when an object falls toward Earth. It's pulled downward by the force of gravity. There is an opposing force to that. So when an object falls, there is something called air resistance. It opposes the motion of that object. So it's going opposite of the direction of that. So air resistance can occur. Causes objects to fall at different speeds, different accelerations, based on air resistance. All right. All objects, gravity will pull on objects all at the same amount, but objects fall at different rates, not because of their mass, not because of their weight, but because of the size that they are, because of the shape that they are, because the amount of shape, the shape they have will affect how much air resistance keeps them propped up. So the amount of air resistance of an object depends on I don't know, I put the speed, the size and the shape of the object. Air resistance and not an object's mass is why feathers, leaves, and sheets of paper fall more slowly than pennies, acorns, and apples. All right, so objects fall at different rates has nothing to do with the mass. All objects fall at the same rate. They all fall, if there was no air resistance, they would all fall at approximately 10 meters per second squared. All right, they would all accelerate at that. However, since there is air resistance can catch those air from underneath the objects, catch the objects and cause them to fall at a much slower rate. All right, so that's sometimes often misled. People think all objects fall at the same rate or objects fall at different rates because of their mass. It has nothing to do with that. All right.